In section 7.2, we're going to go over inverses of relations and functions. And today I just want you to be able to find the inverse of a function by graphing. So let's talk about, first we need to do a couple of vocabulary words. A relation is a set of ordered pairs. So that means if you have a point like 4, 3, the order matters. 4, 3 is not the same as 3, 4. So that's a set of ordered pairs. A function is a relation in which every input x is paired with exactly one output y. So let's just take a few steps back and talk about some additive and multiplicative inverses that we did earlier in the year. If we have the number negative 2/3 and we want the additive inverse, we simply say that it's 2/3 because they have to equal 0. If we want the multiplicative inverse, we flip and we say it's negative 3/2 because we want, when we multiply, we want that to equal 1. So keep that in mind as we're doing inverses of relations. So to find the inverse of a relation, you simply switch the x and the y values of each ordered pair. Okay, so we have a relation here, a set of ordered pairs, because if I would flip-flop these, it would make it a different ordered pair. So we're going to graph these and we're going to connect. So let's just write and connect. Okay, so the first one that we want to graph is 0, 6. So let's go ahead and graph that. And then we're going to graph 2, 10. And then 5, 12, 8, 13. And remember, this is a scale of 2. And 10, 13. Okay, so now we're going to connect these in the order that they were given. And now to find the inverse, very easy. Don't make this any harder than it is. We're just going to switch the x values and the y values. Kind of like we flip-flopped the multiplicative inverse, we're going to flip-flop the x's and y's. So I'm going to take all of the x's here and write them down where my y's are. So this is going to be 2, 5, 8, and 10. And then I'm going to take all of my y's and write them up where my x's are. So this is going to be 6, 10, 12, 13, and 13. Alright, so let's go ahead and graph those. We're going to graph 6, 0, 10, 2, 12, 5, and again this is a scale of 2, 13, 8, and 13, 10. All right, now we're going to connect them in the order that we graphed them. And you might be wondering what this line is right here. This is the line y equals x. And what that means is you can think of it a couple of different ways. This has a slope of 1, so you could write it as y equals 1x and a y-intercept of 0. So this would cross the y-axis at 0 and it would have a slope of 1, up 1 over 1, up 1 over 1. The other way you can think of that is whatever y is, x is. So if y is 2, x is 2. So that's 2, 2, 4, 4, 6, 6, and so on. All right, now we're going to talk about the domain and the range of our relation. This is the relation, the first one that we graphed. And we want to know what the domain is, and we're going to write it in set builder notation. So the set of all numbers x such that x is going to be between two different numbers. So let's look and see. Right here, there's no x value that's less than 0, and there's no x value that is greater than 10. So we're going to say that x is greater than or equal to 0, less than or equal to 10. Now for the range, we look at the y value. So we're looking here, smallest value we have here is 6. So the set of all values y such that y, it's going to be greater than or equal to 6, but it's going to be less than or equal to 13. Because that's as high as it goes on the y-axis, up to 13. Okay, now because we switched the x's and the y's, our domain and range are going to flip-flop. So our range now becomes the domain. So we said the set of all values x such that x is less than or equal to 13, greater than or equal to 6. It's going to make this a little darker so it doesn't look like 16 here, and that doesn't look like 10. And then we bring the range down here. So the set of all numbers y such that y is less than or equal to 10, greater than or equal to 0. Okay, you have a you try it to do on your own.